The previous video discussed sinusoidal forcing. In this video, we want to look at something special that happens in the particular case of when your system is undamped. Okay, so let's take a look at, there's going to be some new ideas here, but let's just jump in and just do an undamped problem with sinusoidal forcing just the way we learned in the previous video. Okay, so here's an undamped case, right? There's no dy dt term. In other words, there's no b. So there's no damping. We would expect, of course, on its own to have just oscillations that go on forever. They don't die out, right? So just sines and cosines, no exponential terms. All right, so let's work this out. So homogeneous first. Let's do the homogeneous. We go lambda squared plus 9 equals 0. Lambda equals square root of negative 3, right? So, or excuse me, square root of negative 9, so 3i plus or minus 3i. And so our homogeneous would be a cosine 3t plus b sine 3t. And so there you go, sort of just a typical oscillation. The a and the b would be determined by initial conditions, but 3 is the number that sort of leads to the natural period and natural frequency, right? So the natural period would be 2 pi over 3, and the natural frequency of this oscillator would be 3 over 2 pi. Okay, now we include the forcing, right? So there's also this extra force, and it's the extra force itself is oscillating cosine 4t, so it's got its own frequency of forcing. 2 pi over, or 4 over 2 pi is the frequency of the forcing term. All right, so the way we've learned how to do this as of the last video was we complexify the problem. We turn cosine into a complex exponential, in this case 4it. Ours is the real part of the complexified version, so if we solve this, then at the end we'll take the real part of our solution. Cosine means real part. Okay, so method of undetermined coefficients, we guess d e to the 4it. We guess that it has the same format. All right, well, the first derivative would be 4i d e to the 4it. The second derivative, which actually is the only one we really need in the undamped case, another 4i comes down, so negative 16 d e to the 4it. We plug it in, and we're going to see that in the undamped case, it's actually sort of even easier than the damped case. The complexification is really nice because notice that of the three, our original guess, our first derivative, and our second derivative, only the first derivative had an I in it other than the e to the 4it part. But that doesn't show up when we plug things in, right? There is no dy dt. So there is no I here except in the exponential, but of course those are common and so they cancel. So we just get negative 7d equals 1. We get d equals negative 1/7, and we don't even have to do the dividing by a complex number trick of multiplying by the conjugate, so we don't even have that extra step. So our particular solution for the complexified version would be negative 1/7 e to the 4it. Therefore, the particular solution for our original, remember we said we were going to take the real part. Well, again, we're going to get a little bonus here because, again, the fact that the d didn't have any I in it makes this especially easy. I only really have to sort of break down the e to the 4it part. And by Euler's formula, that is cosine 4t plus I sine 4t. And so the real part would just be just that part right there, the negative 1/7 cosine 4t. And so the final general solution would be -1/7 cosine 4t plus our homogeneous solution, which we had already, a cosine 3t plus b sine 3t. Now, at this point, we would apply any initial conditions that we have and figure out a and b. If I could just do the following, instead of actually working that out, let's assume that we get initial conditions that that end up making a and b equal to 1/4. Okay, so -1/7 cosine 4t plus 1/4 cosine 3t plus 1/4 sine 3t. There are some initial conditions that are such that a and b would come out to 1/4 and 1/4. And let me just kind of fast forward. That's what I want the a and the b to turn out to be. It'll just make what I'm going to show you next a little bit easier. If that's the case, let's just quickly look at a graph of this function. And here it is. So you see we have oscillatory behavior, but it's kind of, the oscillations get bigger and then smaller and smaller and then bigger again and smaller and smaller. So we sort of have a varying amplitude on top of the normal oscillations that we're seeing anyway. Okay, so I wanted to show you that. All right. Now here was the original problem, and here was our solution. And yeah, what I want to point out again is that, remember, the natural, without the forcing term, the natural homogeneous oscillator ended up with cosine 3t and sine 3t, right? And we said that the natural frequency was 3/2 pi. But that our forcing frequency was 4/2 pi. So in other words, the forcing was not in sync with what it naturally wanted to do. It naturally wanted to cycle this many times per second, but it was sort of being pushed this many times per second. Might be easier to think about this if I turn those both into decimals. The forcing frequency is 0.637, and the natural frequency was 0.477. So you see they're a little bit off. This many cycles per second. That's how often the forcing was happening. But this many cycles per second is what it wanted to do. So they were out of sync. Okay, but that's what I want to talk about next. What if we change that 4 right here, right? That 4 is exactly, directly connected to the frequency of our forcing term. And what if we play around with that? And in particular, what if we make that get closer and closer to the natural frequency? What if we make this 4 get closer and closer to the 3? And what happens when the forcing matches the natural frequency? Okay, so to answer that question, let me rewrite the differential equation. Okay, but this time, instead of cosine 4t, I'll put cosine omega t, where omega can be any number, right? So we'll sort of leave this undetermined so that we can see where that omega ends up in our solution exactly, and then we can play around with that number in the final solution. Okay, well, the homogeneous, of course, would not be affected by it. That would still be a cosine 3t plus b sine 3t. That has nothing to do with the forcing term. All right, but now, if I can just kind of quickly go through exactly the same steps as we did before, but with an omega in place of the 4. And I will go a little bit fast, and you can pause at any time if you want to just concentrate on any one step. But here we go. First, we would complexify by turning the cosine into a complex exponential. We make the corresponding guess using undetermined coefficients. The second derivative of that guess a negative omega squared comes out. Before, when omega was a 4, that was the 16, but of course now it'll be omega squared. I plug the guess and the second derivative into the differential equation, setting it equal to the forcing term. And after canceling the exponentials, I end up with this algebra equation, which tells me that d would be 1 over 9 minus omega squared. Okay. And so, my particular solution for the complexified one is 1 over 9 minus omega squared e to the I omega t. And so my particular solution, so remember, was cosine, so we want the real part of this. And again, very nice in the undamped case, this part is just a real number, so it's really just the real part of the complex exponential, which is just cosine. So we get 1 over 9 minus omega squared cosine omega t. So that's our particular solution. So that, along with the homogeneous solution, gives me a final solution of this. Okay, so now this is what we want to graph. We want to graph this for different values of omega. And in particular, what we really want to see is what happens when omega gets closer and closer to that 3. So again, we had this for omega equals 4. In fact, you can see if you put in a 4 for omega, you get a 4 here, and here you'll get 9 minus 16. You'll get that negative 1/7 that we got before. Okay, but this is more general. For any omega in the forcing term, this is what our solution will look like. And once again, just so that I can graph something specific, if I could just assume that our initial conditions gave us a and a b of 1/4 and 1/4. Again, just to not spend too much time working on that part. Again, let's assume we had some initial conditions that ended up putting a 1/4 and a 1/4 in the a and the b slots. Okay, so now, yeah, let's graph this. And on the Desmos.com graphing page, it's nice because what you see now is I'm showing you our formula, but with well, I use W rather than omega, but W is a good substitute. Our omega is in there now, but I have omega equal to 4, and I have a little slider here that can make that W change dynamically, and we'll immediately see what happens over here. So this was the old picture, right? Because I have omega equal to 4, which is that original one we did. All right, now if I change omega and actually sort of move it bigger, so further away from that 3 that we're kind of really interested in. So if I make omega go higher and higher and higher, okay, we're just getting various changes. Sure, nothing special is going on here. Let me move it back to 4. Okay. Let me zoom out just a little bit. Okay, I zoomed out a bit, but you still see that same behavior as we saw before. And now I'm going to let my slider approach 3. And we're going to see some interesting things, hopefully. So 3.9, 3.8, 3.7, 3.6. Now this is interesting. Let's stop there. Now what you see, right, you see the oscillations, the regular oscillations, but the amplitude itself seems to be oscillating big, and then small, and then big, and then small. So we have sort of 2 oscillation patterns on top of each other. Okay, so what we see here, this is called beats. This is beats, because you have the regular oscillation, and then, like I said, you have the amplitude getting big and then small and then big and then small at a sort of at a less often pace, right? So at a lower frequency, this big, small kind of thing. And the reason it's called beats, okay, I'll try to do this. When sound waves act like this, right? A typical sound wave, our ear just hears a note, right? But the amplitude kind of corresponds to the volume. So a bigger amplitude would be louder, a less amplitude would be lower. So think of the individual little oscillations as a particular note, but what we have is sort of louder and then softer and then louder and softer. So what you get is kind of like a wow, 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 wow kind of thing. And that's called beats. If you've had a physics class, you may have learned about beats there as well. So this is a common thing. So it's like a wah-wah kind of sound where it gets louder, softer, louder, softer, louder, softer, but at one note. And so it's called beats. And that's the behavior we're seeing. Now this is when omega is not quite at the natural frequency of 3, but it's getting closer. And if I move it closer and closer and closer, so I'm at 3.3, you see these beats are getting more and more pronounced. They're getting longer. 3.2. You also see that the overall amplitudes are getting bigger. The peak amplitude of the beats is getting bigger and bigger. Again, if I back up a little, right, you see that. Now I'm at 3.2. There's 3.1. Now I'm seeing sort of one large beat filling up my page. If I zoomed out more, you could see maybe a couple of these beats. But then here we go. If I go to 3, now of course if I go to 3, my formula fails me, right? Because I'm dividing by 0 in my formula. 9 minus omega squared, if omega is 3, fails. So I never could have gotten to this point if omega actually was 3. But here it was right before, and actually I can do on the other side 2.9, similar thing. On the other side, I get the beats as well if I'm lower than 3. So, interesting behavior, but it's sort of, okay, what happens right at 3? We can't tell from this formula because this formula does not apply. The formula that we found doesn't exist when omega equals 3. There is another solution. The solution when omega equals 3 is a separate issue. That requires a special approach that we need to talk about. But I wanted you to see this approaching, the approaching 3 for omega. So again, the idea here is that this is what's happening when our forcing frequency is approaching the natural frequency, and they're getting more and more in sync. Yeah, so to summarize, as the forcing frequency approaches the natural frequency, we see this beat phenomenon, and we also see the amplitude increasing, right? Because as these two things get more and more in sync, they're going to reinforce each other, and it's going to oscillate in stronger and stronger. That amplitude is going to grow because the forcing is happening right in sync with the way that the oscillator wants to go naturally. This is exactly what happens when, if you are pushing somebody on a swing, right? They're going back and forth in a natural way. If you time your swings, if you're the pusher and you time your pushes so that they are in sync with the swinger, of course you're going to make the amplitude go higher and higher. You're going to make the person on the swing go higher and higher, further and further. If you push at the wrong times, sort of not at all in sync, so like, part of the time you're pushing when they're coming back at you, right? Obviously you're going to screw things, you're going to screw up their natural swinging, and you're going to get a mess. It's not going to amount to much, and of course you're never going to get them going very high. But if you time your swings, your pushes, and you're in sync with the swinging, then you can get them going really high. So that's what we're seeing here. It is also the case, as I've mentioned before, if we think of sound waves act like this, right? So if you think of a crystal glass actually, if you ping it, right, it will vibrate at a certain frequency, at a certain note. You'll hear a certain little note when you ping a crystal glass. Now, if an opera singer comes in and sings, well, if they sing at the wrong note, nothing happens to the crystal glass, because the vibrations of the opera singer's note are not in sync with the crystal glass's natural tendency to oscillate at a certain frequency. But if that opera singer hits just the right note or close to it, if the opera singer gets really close to the natural frequency, then the glass will start to vibrate. Its amplitude will get bigger and bigger over time, and if we're close enough to the natural frequency, the glass will shatter, because the amplitude will get bigger than the glass can actually withstand. This is called resonance. So actually resonance, what we've seen so far is near resonance. Resonance itself is when the forcing frequency exactly matches the natural frequency. Now, like I said, we haven't actually seen that. That would be when omega equals 3, but when omega equals 3, the formula we found so far isn't a solution to the differential equation because it doesn't exist. So we still have yet to figure out that that formula, but it's gonna, you can see what was happening. So we should expect something right when omega equals 3. We should see something with growing amplitude. So even at 3.1, it's growing, but then it comes back down because eventually there's a little bit of a difference. So eventually the forcing gets out of sync a little bit for a while with the natural frequency, but then it will come back. I mean, yeah, let me zoom out just one more time. Let me really zoom out. Boom, there we go. So yeah, you can still see the beats. The amplitude is pretty big, and even at the low part of the beat, it's still pretty big, and then it gets even higher. So we still have the beats happening, right? That's a really zoomed out version. And that's at 3.1. Okay, but what's going to happen at 3? Okay, we need to go back to the drawing board and get a new formula for the exact resonance case. I'll do that in a separate video because this video is already a little bit higher. But yeah, that'll be the sequel to this video. Okay.